Hi guys. So in our prior gas law videos, we talked about Boyle's law, how when pressure increases, volume decreases, or if we increase the volume, pressure decreases, right? That they're indirectly proportional, and we got an equation for that. And then we talked about Charles' law and how volume and temperature are related, so that if temperature increases, the volume increases, and if the volume decreases, then the temperature is going to decrease, and how they are directly proportional to each other. And we got an equation for that. So now we're going to look at Gay-Lussac's law. And this one is we have a constant volume and we're relating pressure and temperature. So we had pressure and volume, and we had volume and temperature, but we haven't had the relationship between pressure and temperature. And it makes sense based on the prior formulas that pressure and temperature would be indirectly proportional. So as we increase the pressure, directly proportional. Pressure and temperature are directly proportional, directly related. So if pressure increases, temperature increases. And so we see the formula right here that we're going to take our initial pressure and divide it by the initial temperature, and we will get our final pressure and divide it by our final temperature. And we can rearrange this formula any way we need to solve for any of these. So if we need to figure out our initial pressure, but we have the initial temperature and the final pressure, final temperature, then we're going to multiply both sides by the initial temperature, and we can solve for that initial pressure. Now this is if volume is constant, right? When we bring all these things together, volume, pressure, and temperature, then we end up with the combined gas law. And this is that everything is changing. The pressure is changing, the volume is changing, and the temperature is changing. So we do see here that we're leaving the number of molecules the same, which means we're not putting any more gas into the container, but we are changing pressure, volume, and temperature. So a good example here would be like a balloon, right? We fill the balloon up, let's say, with carbon dioxide, right? We blow into it with our breath, and we tie the end of the balloon. That balloon now has a constant number of molecules of carbon dioxide in it, right? But we can change the temperature of that balloon. We can squeeze the balloon and change the volume. We can, and that would also increase the pressure. If we heat the balloon, right, the temperature is going to increase, and that's going to make the balloon expand. That's going to make the pressure increase. So we can see how all these things relate together. And we see the combined gas law formula right here is really just combining Boyle's law formula, Charles' law formula, and Gay-Lussac's law formulas together. It is literally combining those formulas. So we see those here. Okay, let's look at an example here using a cylinder. We like to use a cylinder with a piston so that the volume of the cylinder can change. We don't want to use a hard structure that the volume can't change when we change the temperature or the pressure. Well, unless we make it explode, right? Not quite the same thing. So here we see we've got a cylinder with a piston so that this top can move up and down to change that volume. We're starting off with 1 liter of a gas, and it's got 1 atmosphere of pressure in there. So that's our volume and our pressure, and we're at a temperature. And we heat it up. And when we heat it up, we give those gas molecules more energy, more kinetic energy. Remember, temperature adds kinetic energy to something, to those molecules. And so those molecules start bouncing around. They have more energy, and so that's going to increase the pressure. So if we keep our piston the same, then our volume is going to stay the same and we're increasing that pressure because those molecules are moving around more. Pressure is actually a measurement of the collisions that the molecules have on the side of the container. So if they're heated up, they have more energy, they're hitting the walls of that container more. It's kind of like when you give Miss P caffeine and sugar, right? I get more energized. My classroom is only so big, but I have more energy, so I'm walking around the room more, right? So that's what's going on here. Or we can keep the pressure the same and make the space bigger so that those molecules have more room for that energy to bounce around in there. And so the pressure isn't going to increase, but we see the volume increases. We can also have a combination of somewhere in the middle. We can have the volume increase somewhere between 1 liter and 2 liter, and the pressure would increase somewhere between 1 atmosphere and 2 atmospheres. So here we show just the volume changing. Here we show just the pressure changing. And here if we let volume and pressure change, then they're both going to change a little bit. And this is all in response to the increase in temperature, giving those gas molecules more energy and therefore having more collisions on the walls of the container. Okay, so here we see combined gas law is, like we said, it contains all the other gas laws, Boyle's, Charles, Gay-Lussac. It's bringing it all together. And we can just remember the combined gas law. We don't need to remember those 3 individual formulas because this one is it all together. And if for some reason one of those things is held constant, temperature, pressure, or volume, we just remove them from the equation. So here we see we have our combined gas law, and our scenario is saying if the temperature remains constant, but we're changing pressure and volume, then we're just going to remove temperature from the equation, and we see we end up with Boyle's law there. The initial pressure times the initial volume is going to equal the final pressure times the final volume. All right, okay, so let's do an example together. Here we have a 15-liter cylinder of gas at 4.8 atmospheres of pressure and 25 degrees Celsius. So this right here is all initial conditions, okay? So this is going to be our V1, our P1, and our T1. And then we heat it to 75 degrees Celsius and compress it to 17 atmospheres. So we have these guys. This is our T2 and our P2. And we want to know what is the new volume. So that's the one that we're figuring this out for. So we make our little list. We write down all our initial things. We write down what we're looking for. And we're going to rearrange our formula to solve for that final volume. So this is our original combined gas law. We rearrange it to solve for V2, which means that we need to take T2 and pop it over to the other side. So we're going to multiply both sides by T2. And we need to get rid of P2, so we're going to divide both sides by P2. So we end up with this. And then we take all that information and plug it into our formula there, pop it in our calculator, and we see our new volume is going to be 4.9 liters. Now, a little mental check that we can do to make sure we did this right is we can say, okay, we're solving for volume. We know that if pressure increases, volume decreases. So we're going from 4.8 atmospheres to 17 atmospheres. We are increasing the pressure. That means that we're like squeezing in on something. So that means that the volume should be smaller. We see our initial volume as 15 liters, and now we're going down to basically 5 liters. And so it is decreasing. All right, let's look at one more example here. Oh, need to shift my screen a little bit. Okay, so Ginny buys a 5-liter helium balloon at King's Dominion when the temperature is 40 degrees Celsius. What will the volume of the balloon be when she gets back to Chantilly, where the temperature in her nice air-conditioned house is 25 degrees Celsius? So we look and we see what is our initial information. Here we have the initial volume and we have the initial temperature. Do we need pressure? No. Pressure is constant. We're not talking about pressure at all. So we want to know what the final volume will be with this final temperature of 25 degrees Celsius. So we make our list again. We do need to add 273 to our temperature to get it to Kelvin. Remember, we want Kelvin because we're at standard temperature and pressure. So we add 273 to get our temperature to Kelvin. Here we have our combined gas law, but we are not using pressure, so we can go to using just V over T. We can get rid of the pressure there, the P. So we can either rearrange our formula, so we're solving for V2 and then plug it in, or we can plug in our numbers and solve for V2 that way. So this is looking at this a little bit differently than our prior problem where we rearrange the formula first and then put the numbers in. Here, we're putting the numbers in and then rearranging it. So when we go to do this, we would have our V2, our final volume, is going to equal 5 divided by 313, and then we're going to multiply both sides, right? 298 is the denominator, so we're going to multiply the other side by that. And when we do that, that should be a 9. Hello, 9. 298. When we do our math there, we get a volume of 4.76 liters. So basically, we've taken a warm balloon and we've cooled it. When we reduce temperature, our volume should reduce. Right? When we put something that's warm and we put it in the refrigerator, it's going to contract. And when we take something that's cold and we heat it up, it's going to expand. So because we've cooled something, the volume should be less. So here we see our original volume's 5 liters, and in that nice cold apartment, it's 4.76 liters. So it lost a little bit of volume. So that balloon, the King's Dominion, is going to be a little bit smaller in Ginny's apartment. All right, guys, good job. See you next time when we talk about ideal gas law.